Welcome friends. In this video, we will be discussing curve fitting and its theoretical concepts. Okay, so let x1, y1, x2, y2, etc. xn, yn be n pair of observations of related data. The general problem of finding a relation of the form y equal to f of x which fits best to the given data is called curve fitting. So I'll explain that using this figure here. Suppose you are having say some set of observations corresponding to this value x1 here. You are having this observation say y1. So this is our observation x1 y1. Okay, this is my observation x1 y1. Corresponding to x1, my observation is y1. Okay, now corresponding to this point x2, say I'm having my observation y2. So this is x2 y2, etc. Maybe this is my last observation, so this is my observation corresponding to xn, so it is xn yn. So I have this data with me. Now the question is, how can I model this data? That is, can I fit a straight line to this data? The question is, can you get a function or can you get a straight line of the form y equal to a plus bx which suits this data? That is, if I substitute xi here, I should get my yi. That is, y1 should be equal to a plus bx1, something like that. If not equal, at least near to that value. So is there a function which can actually model this data? Is there a function which can stimulate this data? That is, in the sense that, is there a function y equal to f of x? In general, here I've taken the example of a straight line. Is there a function y equal to f of x which can give me these desired outputs? Okay, that is, if I substitute my x values into this function, I should get my corresponding y values. Okay, so sometimes what will happen is you may be able to get a straight line which suits this observation. That is, there will be errors, but there which is near to this. That is, suppose if I substitute x1, I'll get my y1. Suppose if I substitute x2, I'll get my y2. Suppose if I substitute x3, I'll get my y3, in that sense. Okay, so sometimes what will happen is I might have to go for a curve, something like this, which fits the data properly. Okay, so the question is there a function y equal to f of x such that if I input my x values into it, I'll get my outputs yi's. I have a data, but it should this given curve that I'm fitting should best fit my data. That is, it should, our values, output values should be as close to our observations as possible. Okay, now let's look at this given thing here, this given data. So suppose time and height of dropped object. So now for to this data, suppose if I fit a curve like this, okay, suppose if I fit a curve like this, then it will give me the desired result. That is, I will be able to fit a curve like this. It won't be a straight line, but I'll be able to fit a curve like this, so such that if I input my xi value, I'll get my yi value. Now here in this, suppose if I try to fit this using a straight line like this, then the thing is, it will pass through some of these points, but it may not fit into all of these points. There will be some error, and maybe something like this may be a better approximation. We don't know. Here also, suppose sometimes I may be able to fit a straight line like this. In this fourth one, I may be able to fit a curve like this, which passes through most of these points. So geometrically speaking, I am trying to fit a curve, okay, which sometimes it may pass through some of these points. Sometimes the thing is, it may be, the points may be as close to this curve as possible. This curve is not fixed. I'm trying to fit a curve such that my observed values are as close to this curve as possible, and some of these points may be on this curve itself. Okay, for example, in this first figure here, if I fit a curve like this, all these points will be on that curve. Okay, here if I try to fit a straight line like this, maybe one or two or three points may be on this straight line, other points are not on the straight line, but the difference is, error is very less. Okay, here also, suppose if I fit a straight line, it may pass through 2 or 3 points, but other points will be will not be on that line, but just near to that line. Here if I suppose fit a curve like this, then what will happen is most of these points, it will pass through most of these points, but the other points will be just near to this. So the question is whether we are able to fit, or how can we fit a curve to a given data. Okay, so towards this direction, the first thing that we will be trying is whether it has a linear relationship, whether we are able to fit a straight line to this given data. That is, whether there exists a straight line which can give these outputs. Okay, so that method is actually called the method of least squares, or the principle of least squares. Okay, so given the data x1, y1, x2, y2, etc., xn, yn, let y equal to f of x be a best fit curve. Yi is called the observed value of y corresponding to xi, and f of xi is called the expected value of y corresponding to xi. I'll explain these using a figure. Let ei is equal to yi minus f of xi. That is the error. Ei is called the error or residual for yi. The principle of least squares states that for a best fit curve, the sum of squares of residuals is a minimum. That is, E is equal to summation I from 1 to n yi minus f of xi the whole square is a minimum. Okay, so let's say I'm having these many data. Okay, so that is, this is my data x1, y1. This is my data x2, y2, second point. This is my third point x3, that is my input, and output is y3. So these are the observed values. Okay, and suppose I'm fitting this straight line y equal to a plus bx. It need not always be a straight line. It can be any curve. It can be a plus bx plus cx square, anything like that. But here, suppose it be a I'm assuming it be a straight line. Then this is the straight line. So corresponding to this point x1 here, this x1 y1 is the observed value, and this is my f of xi. That is, I am fixing this curve. So this is y equal to f of xi. Here it happens to be a straight line. So I am fitting a curve y equal to f of x. So this is f of xi. So this value is called the expected value, and this value x y1 is called the observed value. Similarly here x2 y2, this is the observed value. Okay, but the expected value is here. So if you look at it, that corresponding to y2, this is my x2, but the observed expected value is f of x2. Here it happens to be a straight line, that's all. Similarly, this is my f of x3. Okay, so this is my expected value x3, y3. Y3 is the observed value. Now the thing is, the difference between these 2 points is the error. Okay, so if you look at it here, this value, this is the error E1, difference between y1 and f of x1. And here in this case, this is the error, the difference between that is y2 and f of x2. In this case, this is the error, the difference between y3 and f of x3. So in general, yi minus f of xi is called the error. Okay, now the principle of least squares says that the sum of the squares of these errors should be minimum. That is, summation I from 1 to n yi minus f of xi the whole square should be minimum. So this is what we'll call the error, and this should be minimum. That is what the principle of least squares says. Okay, that it says that this error should be minimum. We should find a curve such that this error should be minimum. I've explained it using a straight line. It can be any curve. Okay, so this error should be minimum. That is what the principle of least squares says. Now for this, we need a little bit of calculus. I'll just explain that calculus part first. Okay, so suppose if I have a function like this, y equal to f of x. You've studied in your plus 2 classes that to find the minimum point or maximum point, the first step that you have to do is you have to calculate dy by dx is equal to 0. Okay, now if this derivative, so the minimum or maximum will occur at these points where the derivative is equal to 0. So you will get a collection of points. Now if that second derivative is greater than 0, then it is going to be a point of minimum. That is, that function is going to have a minimum value at that point. Similarly, if we take functions of more than one variable, that is two variables like this, then you will have to move on to partial derivatives. Okay, so this is the notation for a partial derivative. Here this is just an ordinary derivative because there is only one independent variable. Here there are two independent variables. So correspondingly, here the theory is, if we have to find the collection of points such that dou f by dou x is equal to 0 and dou f by dou y equal to 0. Both these should be equal to 0. RST is the second derivatives of them. If RT minus S square is greater than 0 and R is greater than 0, we say that it is a relative minimum. You don't have to much bother about this part. This is the part that we will be using. So what I'm coming to say is that the minimum for a function of several variables will occur at the critical points. So what are the critical points? The critical points are the collection of points such that dou f by dou x is equal to 0 and dou f by dou y is equal to 0. Okay, now how to find dou f by dou x? Suppose if I'm having some sort of a function like this, f of xy equal to x square plus y square, then you must plus, say I'm saying 2xy. Then when I'm differentiating with respect to x, suppose if I'm differentiating with respect to x, I have to treat all terms involving y as a constant. So it is d by dx of x square is 2x, dou by dou x of y square, dou by dou x of y square. So when I'm differentiating with respect to x, I have to treat y as a constant. So this term will come out as 0. Plus I'm differentiating it with respect to x. So 2y is a constant and dou by dou x of x is 1. So this output will come out as 2x plus 2y. Similarly, when you are partially differentiating this function with respect to y, you will get dou f by dou y. So that is, when you are differentiating with respect to y, you have to treat terms involving x as constant. So dou by dou x of dou y of x square is 0. X square with respect to y, it is treated as a constant, so 0, plus d by derivative of y square is 2y, plus derivative of 2xy. That comes out to be, see, 2x is a constant and derivative of y is 1. So that is 2y plus 2x. So it comes out something like this. Now we will use this method here. So the principle for fitting a straight line. This is the first topic. So suppose we are given with a data, say x1, y1, x2, y2, etc., xn, yn. We are trying to fit a straight line. So we will find the equation so that we can fit a straight line to the given data. So you look at this here, y equal to a plus bx. We are trying to fit this straight line to our given data. So let y equal to a plus bx be a best fit straight line to the given data xi, yi, where I equal to 1 to n. Then this is the residue, or this is the error, that is e equal to summation I from 1 to n yi minus f of xi. Now here our function f of xi is a plus bx. Okay, we are trying to fit a curve y equal to f of x. So our function here is a plus bx. We are trying to fit a straight line. So instead of f of xi, I can replace it with a plus b into xi. So minus sign is there common outside, minus of a plus b into xi. So it comes out as minus a minus b into xi, the whole square. I hope this is clear. In general, we are trying to fit a curve of the form y equal to f of x. Okay, here f of x is a straight line a plus bx. So yi will be equal to f of xi, which is a plus b into xi. We have just substituted that here. Now, according to the principle that we discussed, we are going to solve for this. Now, the thing is, here you see y and x are, although we use, in generally we use x and y for variables, here x and y values we have it with us. A and b, those are the unknowns here. Okay, that you must remember. We want to find a and b such that y equal to a plus bx best fits our data, and our data is given in terms of x1, y1, x2, y2, etc. That is, it is given in terms of xi, yi. So we will, according to the principle that we discussed, its first derivatives should be 0. So for e to be minimum, dou e by dou a should be 0 and dou e by dou b should be equal to 0. So when I'm differentiating it with respect to a, I can treat all the other quantities as constants. Okay, so what is derivative of this term? So you have some term the whole square, so derivative will be 2 times yi minus a minus b into xi into dou by dou a of this term. So this is a constant, yi is a constant, b of xi is a constant. Both those derivatives will be 0, and dou by dou a of minus a, that comes out to be minus 1. Okay, derivative, when I'm taking partial derivative with respect to a, yi is a constant, bxi is a constant. Both those derivatives will become 0. So the only derivative I have to take is with respect to this minus a. So dou by dou a of minus a. So what is derivative of minus a with respect to a? It is minus 1. Okay, so here this minus 2 I can take common outside, so I will cancel it out on both sides. Right hand side is 0. Okay, so here what will happen is you will have something like this. This minus 2 is common, so that I am eliminating from both sides. So minus 2 is common in the sense that it can be taken outside and the right hand side is 0. So it will just come out as summation of yi minus a minus bxi. Okay, so I can take this term to the right hand side. Okay, minus 2 was there common outside, that since the right hand side is 0, suppose I'm dividing throughout by minus 2, this term will get cancelled. So summation yi, if I take the other terms to the other side, it is summation of a plus b into xi. Okay, now summation yi, now summation a, that is a times this summation actually runs from I equal to 1 to n. Okay, so a times summation I equal to 1 to n of 1, that is plus b times summation xi. Okay, now if I'm adding 1 n times, I'll get n, right? 1 plus 1 plus 1 plus 1 n times, I'll get n. So na plus b summation xi. Okay, so that is what is given here, summation na plus b summation xi. Now dou e by dou b equal to 0. Suppose if I'm finding the partial derivative of this with respect to b. So this is the only variable here, b. All the other terms are constant. So dou by dou, so what happens? We have some term square. So 2 times yi minus a minus bx the whole square into dou by dou b of this term. Okay, so dou by dou b of yi is 0, dou by dou b of a is 0, dou by dou b of minus bxi. So that comes out as minus xi. That is what is given here. 2 times that quantity into minus xi equal to 0. Now here again I can cancel out 2. Then what I'll have is on the right hand side I'll be having something like this. Summation yi minus, sorry, I have to first multiply this xi inside. Okay, this xi minus 2 I'm taking it outside, so this xi will be there. So suppose I'm writing minus 2 into summation xi yi minus a xi minus b xi square. I've multiplied that, so this is equal to 0. Okay, now this 2, if I divide throughout by minus 2, it will get cancelled. So I'll be left with summation xi yi equal to summation, I'm taking these terms to the right hand side. So summation axi plus summation bxi square. So a is a constant, I can take it outside. I mean, it's not a constant in that sense. This summation actually runs from I equal to 1 to n, and a does not have any I term. So a can be taken outside. So it will be a summation xi plus b into summation xi square. That is what is given here. You can see it here. It is given like that. Summation xi yi equal to a summation xi plus b into summation xi square. Okay, now these equations 1 and 2 are called the normal equations. Okay, so suppose if I solve these two equations, so here what I'm actually getting is, xi will be given as a column, yi will be given as a column. You can find summation yi, you can find summation xi. Let us add that columns. This data will be given to you. Now xi, you just multiply the second column yi by xi and find summation xi yi. And then you find all these terms, and then what you can do is you can substitute all of them in these two given equations. Okay, that is, you can substitute all of those. So I'll just explain it using something like this. Just I'll make up a data like this. So you'll be given this data to you, say xi yi. So say xi is given like 1 2 3 something, then 9 8 something. Okay, so you can add up this data. This is summation xi, This is summation ya. Now if you need summation xi ya, you just take it like this. You make another column, multiply. So this is summation xi ya. Then you will have xi square, etc. So you can find all those terms because that data is given to you, and you substitute it in these two equations, and you can solve for a and b. So you'll get two equations involving a and b. Sometimes you'll get something like this: 2a plus 3b equal to 5, 4a plus 6b equal to 2, something like that. And then you can solve for a and b, and that you can find. So these are called the normal equations for finding fitting a straight line to the given data. Okay, so the problems based on this will be done in the next class. So what you have to do is we will need these two normal equations to actually solve that. Now there is actually a very simple way of writing these normal equations. Okay, it is not so complicated. Suppose you want to fit the data, that is, you have to fit a straight line y equal to a plus bx to this given data. Okay, the first normal equation is, you just take summation throughout, you will get the first normal equation. So summation y equal to a times, so summation a, that is, you are adding a n times, so that is equal to na plus b summation x. This is the first normal equation. For finding the second normal equation, what you have to do is you just multiply this throughout by x and then find the summation. So you'll have xy, equation 1, you multiply this equation, say equation star. Okay, so x into y equal to a into x plus b into x square. I've just multiplied that equation throughout by x, and then you take summation. So summation xy equal to a summation x plus b into summation x square. So this is the method in which you can write the equations, these two normal equations, very easily. So how to do problems using this, that we will be discussing in the next class. Thank you.